Negative mass is an idea that comes up in some exotic theories of physics and sometimes in science fiction. But it's hard to figure out how it would work if it existed. If you tried to conceptually figure out the behavior of a negative mass object, you're likely to get impossible results, like passing through an object that's pushing against it, or disintegrating from internal elastic forces. At least to start with. In this series, I've been showing how, if you analyze the situation more carefully with the mathematical tools we learn in physics, you start to see that maybe negative mass isn't so weird after all. In fact, many things that you would think would work backwards, like gravity, friction, and elastic forces, actually work close to normally, because the forces are also reversed. Some of these things we can even prove mathematically by plugging negative numbers into the equations of motion. But I couldn't solve all of the puzzles this way, and that largely comes down to the fact that solid objects aren't really solid, but rather are made of atoms. So figuring out how real objects would behave with negative mass comes down to figuring out negative atoms. And so, to cap off this series, that is what I want to try to do in this video. But first, I want to take a moment to appreciate the journey of mathematical discovery that this series has been. I started this video series to answer a simple question. How can negative mass move backwards in response to a force if the object that's pushing it is in the way? It sounds paradoxical. Other people have made YouTube videos about negative mass, and while it's not the kind of thing that produces scholarly papers, a very small number of scientists have written papers about negative mass. But in both cases, they either didn't address this question, or they suggested that negative mass must have some magical, infinite armor-piercing powers because it has to go through the thing that's pushing it no matter what, because the math says so. And yet, most of them said this with a minimum of equations. I wasn't satisfied by this. I didn't have the numbers to back it up at this point, but something just didn't feel right. Shouldn't the structural strength of the negative mass object matter? Where does the actual force to tear through the armor plate come from? What if we make it a Physics 101 problem, where the objects aren't allowed to bend or break by fiat? When I was just trying to answer these questions conceptually, I was as lost as everyone else. The solution was math. Instead of trying to imagine how objects would behave in ways that made sense, I abandoned my assumptions and plugged negative numbers into the equations to see where they led. Others, including the founder of this contest, have talked about the process of inventing or discovering math, whichever description you prefer. This video and this series aren't that. I didn't define a function or invent a new distance metric here. I certainly didn't make things mathematically rigorous with epsilons and deltas. Instead, I focused on simple algebraic equations and low-level calculus. And don't get me wrong, there's a place for covering those topics, but they're not exactly new. But what is mathematically new here is that I used those equations in ways that physicists almost never do. Maybe that no physicist has ever done professionally. At least not that I could find from my literature search. Like I said, it's not the kind of topic people write papers about. I tried to dig some up, but the number of papers that looked at negative mass in terms of classical mechanics, like these videos do, was literally in the single digits. And none of them that I found pushed the concept as far as I did and looked at elastic and inelastic collisions by the numbers. And that is what makes this a journey of mathematical discovery, even if it doesn't get into a journal. And of course, I am open to informal peer review through the comments. The surprising answer to my question about objects moving the wrong way under forces is that the negative mass doesn't necessarily move backwards at all. In fact, it can move forward faster by sucking negative momentum out of the thing that's pushing it. That is weird. It defies our expectation for how energy flows. It implies that it's the normal forces that are backwards, which defies our expectations about how things work. It's definitely not something I would have been able to figure out without the math, but the math does work. If you plug negative numbers into the equations, they tell us that the normal forces can be reversed, and that resolves the paradox. And in many cases, this is what a thought experiment is. We think of thought experiments as a physics concept, but they're just as much a math concept in practice. Like Einstein asking what you would see if you rode a beam of light, a lot of thought experiments involve stress testing the familiar equations we rely on in physics to see what breaks. And if it does, what new math can tie it back together. It's not inventing new math, but it is a new application of that math, which can lead to equally surprising results. In this case, stress testing the equations of classical physics with negative mass made normal forces break. But when we accepted reversed normal forces, the behavior of negative mass was less weird than I first expected. It can behave like positive mass under friction, gravity, and sometimes elastic forces too, and you lose the magic armor-piercing result. However, there was one thing that didn't work out that way, which was drag forces. Drag forces, it seems, will still cause a negative mass object to accelerate forward the wrong way. But I only reached this conclusion by modeling the drag force as individual gas molecules bouncing off a much larger solid block, when in fact the block and the gas are both made of molecules. When an air molecule strikes a negative mass block, it's not hitting a solid wall. It's hitting a negative molecule in the block, which is in a lattice with other negative molecules that exert forces on each other. And to figure out what happens then, we have to figure out how negative mass atoms can exist and how they interact. Figuring out negative atoms is hard. In fact, it was the hard part that held up continuing this series for so long. But I eventually did figure out how to go about it, and it involved stress testing the physics equations once again. We'll look at the hydrogen atom here because that's the easiest one, and we can apply the same principles to the other elements. We want to make a hydrogen atom with negative mass, but if we look at the simplest way to do it, we immediately run into problems. The simplest way, the most obvious way, to make a negative mass atom is to take a normal atom and replace each of its particles with a negative mass counterpart. But if we try to put together a negative mass proton and a negative mass electron to make negative hydrogen, it immediately flies apart. Normally, opposite charges attract, but negative mass moves the wrong direction, so the attractive force is reversed, and the opposite charges now repel. And from this, it may seem like our hope of negative atoms can't even get off the ground. But we should consider other possibilities. For example, the repulsion problem could be fixed if we replace our negative mass electron with a negative mass positron. This may sound crazy to we who are used to positive mass, but with negative mass, if opposite charges repel, then like charges attract. The negative mass positron can form stable orbitals just like a positive mass electron, and we have a stable atom. There's just one problem. Now our atom has a net positive charge. We can form atoms and molecules this way, but if they're made with only positive charges, they're not going to play nice with anything, really. If you calculate the electric potential energy and electric field from an object where every atom has a net positive charge, you get numbers that are so big that I'm not sure if I even trust them. Numbers way bigger even than antimatter. So big that I'm worried it's going to break a quantum something or other and the equations will stop working. And no matter what else, you certainly couldn't make stars and planets out of them because they would all collapse into black holes from the enormous electrical energy density. So for building a negative mass atom, opposite sign charges don't work, and same sign charges don't work for anything bigger than a molecule. It seems like we've again hit an impasse, but there's one more trick we can use. We could replace the negative mass electron with a positive mass particle. Now this sounds like it wouldn't work for two reasons. First, it sounds like it's defeating our purpose. We want negative mass. But remember that the proton's mass is 2,000 times bigger in magnitude than the electron. If we flip the electron to positive mass, the total mass is still very much negative. The second problem is subtler. A famous result of negative mass, which I've mentioned a couple of times, is that with gravity, if you mix positive and negative masses, you can get runaway motion, as the negative mass is attracted, but the positive mass is repelled. This is allowed because the total mass is zero, so the kinetic energy doesn't change. It's always zero. And if you apply Coulomb's law to our newest attempt at a negative atom, you get a similar problem. The positive mass electron is attracted to the proton, but the negative mass proton is repelled from the electron. It isn't obvious whether or not this works as an atom. Let's back up for a minute and talk about gravity and gravitational orbits, because it's really the same problem, just with a sign flipped. You may have been thinking up to now that these diagrams aren't how atoms really work. Electrons don't move in Keplerian orbits in atoms. They're spread out through their quantum orbitals. But remember Niels Bohr's correspondence principle that classical motion is the large-scale limit of quantum motion. If we calculate the motion of a gravitational system like a moon orbiting a planet, we should get the same behavior from quantum particles on average. This makes things a lot easier because we don't have to solve the Schrödinger equation. Because the gravitational force has a sign flipped, with like masses attracting, we need to flip the signs on the objects here, so we have a positive mass planet orbited by a negative mass moon. Just like in our atom, the planet is repelled from the moon, but the moon, with negative mass going the wrong way, is attracted to the planet. Does this work for a Keplerian orbit, or do the planet and moon slowly drift apart or something? It turns out that it does work. The analytic solution is beyond the scope of this video. You can look up the two-body problem for yourself. But you do still get a stable orbit. And we can check this by integrating the equations of motion. In fact, we already are. What you're seeing here isn't an arbitrary animation. I'm using an actual orbital integrator to calculate the motion of the planet and moon from the gravitational forces. And it works exactly like Newton's law of gravitation says it should. Except you may have noticed one thing. With a negative mass moon, the center of mass isn't between the two bodies anymore. It's over here. Both objects orbit on the same side of the center of mass instead of opposite sides. It may seem weird that the planet is moving with the moon in a global sense when it should be repelled, but if you look at what it's doing at any particular moment, the planet is falling away from the moon, just like the moon is falling towards the planet, which is exactly what we expect with one negative mass. It seems weird because it's in an unexpected position, but the math works out. The flip side of this is that this does not work if the planet is negative and the moon is positive. Then the moon will be repelled from the planet faster than the planet can catch up to it, and you won't get a stable orbit. By the correspondence principle, these results should also apply to atoms that have the same chasing mechanic. That is, it doesn't matter if the massive proton is repelled. So long as the electron is attracted to the proton, you'll get a stable atom. That gives us one working example, but I wanted to be rigorous about it. Instead of building a model haphazardly like we did before, we should consider the full range of possible atoms where negative mass is allowed. If we do that, the electron can have a negative or positive charge, that is, it can be electron or positron, and it can have a positive or negative mass. Thus, there are 4 possible electron-like particles we can use. Likewise, there are 4 possible proton-like particles we can use. This gives us a total of 16 possible combinations, and it's probably easiest to see what they do if we just simulate all of them, even the ones with positive mass. And here they are. I'm using classical orbits to simulate them here, but again, by the correspondence principle, the result should be the same. These are all 16 possible combinations of protons and electrons. Mass is not to scale. The one in the top left corner is the normal matter we're used to, and the one next to it diagonally is antimatter. And as you can see, 8 of the 16 combinations immediately fly apart. These are combinations where either both particles are repelled from each other, or the much lighter electron is repelled from the proton and rapidly escapes. So we can eliminate all of those for forming stable atoms. Of the remaining 8 combinations, 4 of them have a net charge, which we already saw was unsuitable for macroscopic objects. So these are valid atoms, but not useful for our purposes. Interestingly, after this, everything that's left has positive mass electrons or positrons. If all of the particles in atoms have negative mass, then normal matter as we know it can't exist. That bodes poorly for the possibility of negative matter existing in our universe. You'd expect conservation laws to protest against that. But it doesn't stop us from doing the thought experiment, so let's keep going. Of the 4 combinations of particles that can potentially form macroscopic objects, 2 of them have positive mass, which are the normal matter and antimatter I pointed out earlier, and 2 of them have negative mass, which are sort of a negative mass matter and antimatter. And of these 2, there's only one that we really need to consider. If the negative mass atoms have positrons, they aren't going to play nice with normal matter, so we can disregard that. The end result is that the only negative mass combination that we can use to gauge its interactions with normal matter has a negative mass positively charged proton and a positive mass negatively charged electron. And that is an important and surprising result. Negative atoms, if they can interact with normal matter in a normal way, will do it with normal electrons. What does this tell us about macroscopic objects? Quite a lot, actually. It tells us that the interatomic and intermolecular forces between atoms work close to normally for negative mass. We can keep the same formulas for them because they're still electron on electron, which makes our job that much easier. If you've taken a chemistry class, you probably heard about intermolecular forces. Those are the forces that cause atoms and molecules to stick together even though they're electrically neutral. They're what give water its surface tension and allow geckos to climb windows. And they all have roughly the same form. In general, intermolecular forces, It doesn't matter whether it's a strong covalent bond or weak van der Waals forces. All have potential energy curves that look basically like this. At larger distances, there's a relatively weak attraction force. That's what causes atoms in solids and liquids to stick together instead of boiling off. Then, as they get closer, it flips to a repulsive force with a very steep slope as the electrons start to repel one another. For van der Waals forces, which are the most common basis for normal forces, this is roughly an inverse 13th power force. I don't know why that is. It has something to do with the Taylor expansion of the quantum wave function. But regardless, it's an incredibly steep force gradient that jumps from negligible to overwhelming over a very short distance, which is what lets us treat atoms as something close to rigid classical bodies. This is actually easier than the classical mechanics we looked at in previous videos, because there's not an arbitrary theoretical surface to worry about. The surface is an emergent property of the equations where the forces grow too large for the atoms to pass through. And we can model this for negative mass in the same way. Plug negative numbers into the equations of motion and see what happens. Let's start by just looking at the collision of two atoms in a gas. Here is a xenon atom, one of the heaviest gases you're likely to encounter. And if you encounter a heavier one, there's a good chance it's radon, and you want to stop encountering it post-haste. And here is a much lighter helium atom, the second lightest gas you'll encounter under normal conditions. And much like the proton and electron, we should consider all of the possible cases. This time, both atoms are electrically neutral, so there are only 4 combinations for the positive and negative mass for each. Let's see how each one works. If both atoms have positive mass, they bounce off each other normally. At the speeds atoms move in a gas, the attractive forces don't really matter. It's pretty much only repulsion. If the xenon atom has negative mass, its acceleration is reversed, while the helium behaves normally. Thus, the helium bounces off the xenon, and the xenon is attracted to the helium, moving the wrong way, but it's so much heavier that it moves much slower, and the helium escapes. This matches up with our model of drag forces from Part 3. A solid object moving through a gas will have atoms and molecules bounce off it in a net forward direction as it moves through them. The object will lose momentum to these molecules, which would ordinarily cause it to slow down. But for negative mass, it speeds up. It sounds weird, but the energy still balances out. And here we see that molecular collisions work the same way. If the xenon atom is positive and the helium is negative, this is where things get weird. The xenon is repelled from the helium, but it's heavy and slow. Meanwhile, the helium is attracted to the xenon. And with a force gradient that steep, it's not going to orbit either. When we analyze central forces in physics, we find that in any force gradient of inverse cube or steeper, which this certainly is, orbiting particles fall into the center of the system. Applied to atoms, the separation between them would rapidly drop to 0. You don't have the atoms bouncing off each other this time. They actually do pass through each other, which unlike classical physics is allowed here because they're not really solid. It's notable that this breaks our previous classical analysis that normal forces should be reversed with negative mass. In a classical physics model, a small negative mass should bounce off a large positive one, the same as the reverse. But if we model it with actual negative mass atoms, it breaks the symmetry. The reason for this is straightforward. We've replaced our theoretical normal forces with real electromagnetic forces. If these were classical objects with ideal platonic surfaces, the normal force would be surface on surface, and you could plausibly have it switch direction. But real normal forces are electron on electron. And we've even established that they're both positive mass electrons in this scenario. And the physics says that the forces between electrons don't reverse. Unfortunately, this throws out a lot of our analysis from the previous videos, but I don't think that time was wasted by any means. Much like the pioneers of physics, we had to understand the simpler classical forces before figuring out how to tackle the more complicated forces in real atoms. Even in thought experiments, the scientific method is a process of continual refinement. And this reversal is a natural refinement on the classical theory we explored before. There's a separate issue here that applies in both cases where the masses have opposite signs. We looked at cases where the masses were very different in magnitude, helium and xenon. What if the atoms or molecules are close to the same absolute value mass? Well, first off, it is possible that there's some quantum process where the particles annihilate, like matter and antimatter. Since their total mass is zero, they wouldn't even leave anything behind. That might be more sensible, but it's not as interesting. So we'll assume they don't annihilate. We found in part 1 that when two masses collide, the closer they are to equal and opposite, the more they'll speed up when they interact. That's essentially because the total mass gets very close to zero, in which case the same force can result in larger and larger accelerations. To see how this works, take two nitrogen molecules in air. One has positive mass and has a mass of 28.006. The other has negative mass, and it has a mass of negative 27.992. The difference comes from the fact that it still has positive mass electrons. They're not exactly equal and opposite, so they can't undergo complete runaway motion, but it's very close. If I simulate the equations of motion for this system, how much speed do they gain in the collision? The exact answer depends on how close the collision is. Is it head-on or grazing? But a few % of them will be very close to head-on, and that's more than enough to cause complete chaos. The mass difference is so small, and the force gradient is so steep, that you can find plenty of solutions where the molecules accelerate to relativistic speeds. And you can ask Randall Munroe of XKCD what happens when things start moving at relativistic speeds. Yeah. So it may seem like we're done here. But wait, there's one more possibility we didn't get to yet. And this actually reveals another problem. What if both molecules have negative mass? Under intermolecular forces, they'll both be attracted to each other. Once again, the gradient is so steep that the molecules will merge together, and the atoms within the molecules, and their nuclei will fuse together in short order too. In the end, you'll wind up with one big atom. Add more atoms, and the nuclei will be squished together, and you'll get something close to a neutron star. Unlike our single atom examples before, this superatom as a whole is electrically neutral and surrounded by electrons. But we've still left the realm of normal matter far behind. And with that goes our last chance of making this work. Despite our best efforts, purely negative mass matter doesn't work the way we want it to. Even in an all-negative mass universe, at best you'll get neutronium, and you might just get black holes. Is there a way around this? Could we push the concept of reversed forces further, and do something like flipping the potential energy curve upside down? The problem is, if we do that, we're effectively abandoning Einstein's equivalence principle. Newton's second law, will work differently for electromagnetic and gravitational forces. And if you keep going, I suspect you'll eventually wind up simply treating the inertial mass as positive. You can formulate a theory that way, but it's not the same as the negative mass model we've been using this whole time. This is a different model that is sometimes called biometric gravity, although that term is fraught, so it doesn't apply here. But if we back up, I think there's still something valuable to be learned here. My colleague Fred Adams likes to say that doing thought experiments about other universes helps us better understand our own, and I think that applies here. The way hypothetical negative masses would behave reveals deeper truths about how real forces in our universe work. In the real universe, gravity dominates on large scales. Like masses, which are all masses, attract, and matter clumps together. Normally, electromagnetism is the opposite. Like charges repel, and matter spreads out. All of the like charges are either trying to get away from each other, or they're paired up with opposite charges and not subject to net electromagnetic forces at all. With negative mass, the direction of motion is reversed, and electromagnetism behaves like gravity. Like charges attract, and as we've just seen, this results in the same behavior as gravity, where matter, or at least nucleons, clump together, only much, much faster. Evidently, this is a more general result of attractive forces that can apply in real physics, given the right context. The hypothetical points us to the real. When you mix positive and negative masses together, it gets more complicated. The infamous runaway motion doesn't really have an analog in our universe. But when we analyze it in terms of individual molecular collisions, it becomes clear that even a small number of head-on collisions will rapidly turn any matter into relativistic plasma. So, coming back around to my original question from 2 years ago, what does it mean for an object to have negative mass? We now have an answer. It means that it moves in the opposite direction from forces applied to it, and that's not as crazy as it sounds. In classical physics, the math suggests that the forces themselves can be reversed in order to avoid a paradox of objects passing through each other. That solves my original problem with the idea, and I could have left it at that. But it turns out to be misleading when we look at the real physics of atoms and molecules. That's where things get really weird. Real negative mass matter would behave very differently from positive mass matter. A universe with only negative mass would rapidly turn into neutronium and then into black holes from like charges clustering together, while a universe with both positive and negative mass would rapidly turn into relativistic plasma from runaway motion and collisions. Seeing this, I think we can be thankful that negative mass doesn't appear to be possible in our own universe. But the beauty of math is that you can construct a universe that has it. And even better, from that, we can learn a little more about our own. Thank you all for coming on this mathematical journey with me. It's been a wild ride. Be sure to like this video and subscribe to my channel to be notified about future uploads, because I do have more mathematical content in the works. And be sure to check out all the other Summer of Math Exposition videos, because there's sure to be some great ones out there.